It's always good to be speaking at home. I love to speak in London. It's great to see a lot of familiar faces in the audience as well. So thanks, Devox, for having me here. This talk, I realized a few days ago that the title is a bit misleading. So I won't be talking about functional programming, if that's what you are here for. So probably there is a much better talk by Bruce in another room. So what I found over the years interviewing people, we normally in our interviews we don't ask any technology specific. We normally talk about principles of good software development and design. And we get a lot of people saying, oh, I've been doing object-oriented programming for 10 years. And what normally they mean is that they've been putting some code wrapped by a class. And very few of them could actually express how they use object-oriented programming and object-oriented design, how they model their systems, how they express their domains. So this talk, I won't be making any comparisons between OO and functional. I'm going to be talking about some sort of well-known object-oriented design principles and some not so well-known. And there is this quote from Marcin Oderski. Probably some of you may know. He's the creator of the Scala language. And in one of these Coursera courses, he said that. He said, like, object orientation is a dimension orthogonal to the imperative logic functional dimension. And I tend to agree with that. I think that all these principles of good software design, first of all, they were never really well understood. And now with the whole functional programming hype, they are being totally forgotten. So I don't need this OO thing. So this talk is about bringing that back. And so throughout the talk, I'll be talking about many of the principles. I won't go into many details in any one of them because, like, certain principles, Uncle Bob has a 1-hour video just in one of the slides. So the idea is that you just, hopefully to raise an awareness of the things that you may want to expand upon later on. I will start with class invariant. So invariant is established during construction and constantly maintained between method calls. So very academic example, you take a rectangle and on its own it has height and width. You go there and you have methods like set height, set width. And the invariant of the class rectangle says that height and width can be changed independently. So changing one won't affect the other. And then we have a class called square that we extend rectangle. And in math, square is a specialization of rectangle. However, when we try to model things like that, imagine that this is slightly more complex. Imagine that you have these inheritance hierarchy that I know that many of you working with Java, at least in large systems, you find like 6 levels of inheritance, right? So imagine that this is something like that. So what would happen if we call the setter methods that were inherited? So basically, for the square class, I would be allowed to change height and width independently. And that would break the invariant of the class square that says that the sides should have always the same size. So both classes have invariants. But when we extend, we may break the invariant of the subclass. So we can fix that. We can maybe go to the square class and say, well, every time that I set the height, I'm going to set the width as well. And every time that I set the width, I will set the height as well. And that's a very common thing that we do when we use inheritance, where we want to reuse some code, and then when we inherit the subclass, it wants the majority of the behavior of the parent, but it doesn't work quite like that. And then we start doing things like that. But when we do this, what happens is, now the square class is maintaining its own invariant. But if the square class is used in the context of its parent, it will break the parent invariant, because the client class, expecting a rectangle, we expect that that class will behave that you could set height and width independently. So a lesson here is that in isolation, rectangle and square with this fix, they are both consistently valid. And that's what we do in our subclass. We bend them to satisfy its own invariant. But the invariant rule says that a subclass is not a subclass when it weakens the superclass behavior in order to keep its own invariant. Or state becomes invalid when used in the context of a superclass. And we normally apply the is-a relationship to define an inheritance. So we normally ask, like, is a square a rectangle? If the answer is yes, we say, yeah, that's a valid inheritance. Not always that's the case. Just asking this question, not always is enough. So this whole conversation about inheritance leads us to one of the solid principles. How many of you have heard about the solid principles? Okay, half of you. So Liskov substitution principle is one of the solid principles. And basically it says functions that use pointers or reference to base classes must be able to use objects of derived classes without knowing it. So every time that we do things like that, where the client class needs to know which instance or which inherited class it's using, we are breaking the Liskov substitution principle. So another subtle event back to our square and rectangle. So that's why I said, like, if you change set and width, they will break the invariant, and that will violate the Liskov substitution principle. And so without the fix, height and width can be changed independently. Square would be in an invalid state if used as a rectangle, and then with the fix it would be the other way around. And this is a great quote that I like it. Like, if it looks like a duck and quacks like a duck, but needs batteries, you probably have the wrong abstraction. So that's the core of the Liskov substitution principle. So to fix the design, basically, in this case, modeling the real world is not the best approach. Square should be a class on its own and just have one attribute that is the size. So a very important thing is, when we are modeling, we tend to think in classes in isolation. So this class looks good in terms of behavior, cohesion, all the kind of good stuff. But a model can only be validated according to how it's used by its clients. It's how the client classes are using these domain concepts that we're trying to model. And that's what will drive our design. So having knowledge of these design principles like Liskov substitution principle, it serves as a strong guideline for us to model our software better. And this whole conversation about invariant leads to design by contract. So hopefully I will be able to make a story of how one principle and concept leads to another. It took me a while to figure that out, the relationship between the things. But the environment, the whole invariant thing comes from Bertrand Meyer, 1986, based on the mutual obligation and benefits principle. So it talks about preconditions, postconditions, invariants. So it's the client obligation, supplier benefit. So basically, a client pays a fee, so that's the obligation, and get a product back. That's the benefit. Or a supplier class gives a product to the client, that's the obligation, and gets money back as a benefit. So that's the principle behind design by contract. So when we are modeling our classes or modules or functions, we say, like, what does it expect? What does it guarantee? And what is maintained before and after the operation. So that's the whole design by contract. And design by contract has some implications, mainly when it comes to inheritance. So subclasses are allowed to weaken the preconditions, but not strengthen them. Strengthen post-condition environments, but not weaken them. And that's the foundation of Liskov's substitution principle. That's how they relate to each other. I'll show a violation in here. So we have a class called trade that has a public method says process, and in the middle of this method, there's a few lines, and right in the middle says notify regulator. That's a protected method. And then, according to our business rules, we have a special type of trade. But we want to reuse the majority of the stuff that is being done by the trade. So I've seen these over and over again, even in our own code base. So we try to reuse stuff and say, yeah, but you know what, like these subclass in specific doesn't really need to notify a regulator. And then what we do, we just do this sort. How many of you have seen this sort of stuff? Inherit a method and then just ignoring them. Right, yeah? So more than half of you. And also, because we don't really understand everything that the trade does, but we have some constraints, so what we do is to say, let's add a check in here and say, if something is invalid, just throw a new exception. So in this case, what we are doing in this one here, we are making the post condition weaker, because the client class deals with a trade. It doesn't know that it will be invoked like that. So the client class expects that whichever trade it receives, the regulators will be notified about that trade. And it won't have a clue about this sort of stuff. So all of a sudden, the client class may get a runtime exception without not even knowing what's going on. And that's not really fair to the client. So knowing these things is what leads us to a slightly better design. Another thing that is important is when you unit test, if I unit test both classes, the special trade and the trade, that will be all well and good. They will behave according to the behavior that we require. But it's just on higher level tests that we will see if the classes talk to each other in a nice way. So the validation of the design will happen with higher level tests and not in a lower level test. And there is this thing, because we have this contract of preconditions, and that is totally related to defensive programming. So if you have a precondition, who is responsible for guaranteeing the precondition? So in design by contract, it says that it's the client's responsibility or obligation to respect the supplier's precondition. And code should fail hard. So the client should know that it shouldn't pass a null as a parameter to the supplier class. Defensive programming, normally we do the other way around. We say, I don't know what my clients how they are going to call me, so I'm going to guarantee that I'm going to check for nulls and negative numbers and whatever. I think that there are, you could argue that you could go either way. It depends on what you're doing. The way that I prefer to do it is, if it's internal code, if it's my normal business application, I would always have my clients respecting the contract. I wouldn't use defensive programming. If I'm providing an open source, a framework, or a library that will be used by external clients, I probably will avoid the client to behave in a weird way, and I will tell the client, oh, you passed a no, I don't accept that. So I would use slightly defensive programming in this case. But normally I would always, because otherwise you end up with every single method that has a parameter, you end up with an if statement on top, trying to figure out. And so it's your code. You should guarantee that contract via tests and not cluttering your code with defensive code. Some languages like IFO has design by contract implemented in the language itself, so you can code as part of the language the invariants and preconditions and postconditions, stuff like that. In Java, there is a framework called JContract that you can use annotations to do these things. I personally don't recommend. I don't think that is necessary. And then, of course, we are talking about post-conditions. Post-conditions lead us to side effects. The evil side effects, the evil of OO, and the beauty of functional programming, right? I want to use functional programming because it has no side effects. A system with no side effects doesn't do anything. It's pointless to have, right? If I invoke stuff and nothing happened, what's the point of that anyway? So, yeah, but we need to segregate mutability and state change. Great, that's just good old, that's good design principle. That's not our functional stuff. That's just good principle of software design, controlling your state change. But of course, like the problem, what's the problem with side effects? Well, order of evaluation matters. It makes it far more difficult to understand the code because you need to understand the sequence of steps because the state's been changing. So you need to understand all the previous calls and the next calls and everything else. So, of course, multi-threading is always a problem. And there is this action at a distance pattern that is like very common where you change state in one place and then all of a sudden in a completely different part of the system it behaves in a different way and breaks and so that's one of the problems. So to avoid that, use side effect-free functions whenever possible. This is not related to any paradigm, just common sense. Never use global variables, same thing. You can do that with imperative. Prefer returning a value instead of manipulating a parameter's state. Purely good practice. Localized state change, putting state and respective behavior together. Not so common in functional, more common in OO, putting together. Using the tell don't ask approach, so ask your functions and objects to do things for you instead of getting all these states out and doing the computation yourself. And then immutable class. And then there is this thing, how many of you have heard about CQRS? Yes, some of you. So, CQRS is the command and query responsibility segregation. This recently was incorporated to domain-driven design. Basically, one of the key things about CQRS is having two separate domain models. One for writing, one for reading. So when you have like a form application, then you type in some data and then say submit and persist. Then you can have a very simple model that just does that and persists. And then you can have a different domain according to how you display the data or you send the data out to a queue or whatever that just represents what is needed for the UI or for the queue. So you can split command and query. But this is also, again, good design principle. There's nothing to do with imperative, function, or logical. So side effects, they lead us to principle of least astonishment or surprise. That's another design principle, not very well known. But basically what it says is this can be applied to everything. So even if it's a user interface, that should behave the way we expect. Basically what it says is we shouldn't be surprised by the behavior. It should be clear to us how we should use that UI or what that method or class does or that function does. Basically that's what it means. So Joshua Block says that all programmers are API designers, and I totally agree with that. So we should worry about that. Are we respecting the contracts? Are we providing a code that is easy for people to understand by its name? Does it do what it says in the tin? So there was this violation of the principle of least astonishment. I was working in a system about 2 years ago, and we had a bug that we couldn't find. We spent like hours, I think that a few days actually. It was a very similar example, but far more complex. Like this body had hundreds of lines, calling other methods had hundreds of lines, and then in the middle of the fires of hell, we had a line that would take the parameter that was being passed down and change in the state. And all the code above was relying on the states and doing if states. And it had no idea where the bloody state was being changed. And that's one of the violations of principle of least astonishment or least surprise, is that we were expecting that to process the event, but not to change the state of the event. If you want the state changed, we could throw an exception. We could return the state of the status of the processing. We could throw another event and have a listener to say if it's successful, there was an observer in there, and then listen to the success case or the failure case. So, but never change the state of your parameter, because God knows what's going to break. So this sort of stuff is totally related to another solid principle called the single responsibility principle. There is another, so it's the S in the solid principle. This is the simplest software design principle, and is by far the most violated one. I had a very interesting conversation with a developer, and I confess that I didn't have a good argument. It took me a day to figure out how to explain that. We had a method, said process trade, easy. 52 lines of code, not that huge, still reasonably big. And then we were pairing, and I said, like, this method is doing too much. This is violating the single responsibility principle. And I said, no, it's not. So, well, no, clearly it is. No, it's not. And then I said, like, why is it violating? Well, this does far more things than it says. I said, no, it doesn't. It says process trade, and I have 52 lines processing the trade. I couldn't answer that. Because according to the method name, it was so generic that I could put 3,000 lines in there, and it would still make sense. Right, so I should keep this in my hand. If it worked, it doesn't. So there is, the SRP has this notion, the way I like to put this way, there is the outside view and the inside view. So the outside view is when you look at a class or a method, say, what is its name? What is the name of this class? What is the name of this method? So what do we expect it to do? So that's the outside view. That's the discussion that I had with the developer. Process trade should process a trade. The inside view is, how many reasons do I have to change this method? And if it's more than one, clearly it does more than one thing. So if I want to change how the trade is validated, that's one reason for me to change this method. If I want to change how the trade is enriched, that's another reason to change, and so on and so forth. So you should ask yourself, how many reasons do I have to change this thing? The answer should be one. Another interesting one, about the else keyword. We try to avoid as much as we can. And so, but what is this thing about the else statement? It's because as soon as you have an else statement, you are explicitly saying that if something, do one thing, else, do a different thing. So it may be doing at least two things. So you can solve the else with polymorphism in other ways. So there is another thing about that. That's why this is the simplest principle, but it's one of the most complex to explain, or the easiest to violate. I came to a conclusion. This is more a theory. I'm still working on it and trying to prove that. Imagine that this is the input of your application, whatever that may be. If it's a web page, if it's a queue, whatever it may be. Then it will come through a class that will receive that input, and that will do loads of business logic in here that will delegate, and do loads of business logic and delegate until it gets to the output of your system. So, to minimize the single responsibility principle, one of the things is doing outside the TDD. That means testing each layer. So I would test the behavior of this layer and mock everything else, and then I go to the next layer, test that layer, mocking everything else. So you are designing your code. You're using TDD to design and not to test. You are testing as a side effect, but you are more designing. What is the collaboration of those classes? Where do I want the behavior to be? So that's one thing. The good understanding of different degrees of responsibilities and the delegation ratio, that's what I'm toying at the moment. Because in this flow, from the input into the output, loads of things will happen. There are loads of business rules that according to values or decisions, it will go to a different branch of your code and then a different branch of your code. So how can I have single responsibility all over? It's almost impossible. Unless that we understand what responsibility is. So my theory is that the closer the class is to the input of your system, the responsibility will be more about controlling flow and delegating every single specific behavior. So this will be a coordinator class. It will just delegate the flow. It will control the business flow. But the class on its own doesn't do anything specific. It doesn't parse an XML. It doesn't store in the database. It just delegates, controlling the flow. And this ratio, until it gets into here, this method here, the responsibility will be persist the user in the database. That's a very single responsibility. But there are degrees of responsibilities. One is very specific when it's closer to the output. This one is more coarse-grained, more business-like, more controlling and delegating when it's closer to the input. And then you have some things in between. But we should always try to have this distinction of what commands are and queries are. And that will complement the whole thing. So, single responsibility principle is based on cohesion. Cohesion is many of us learn at university. Almost no developer can explain to me what it is. So, not even myself, I couldn't explain that. I had to read a lot and understand quite a few years back, and I call the cornerstone of object-oriented programming, I even blogged about it. It's my favorite thing in object-oriented design, because everything for me comes, the cohesion is at the center of everything. So, what it means? When the cohesion is when the members of a group or society are united. And cohesive means united and working together effectively. Or in Wikipedia, in computer programming, cohesion is a measure of how strongly related and focused the various responsibilities of a software modules are. We tend to treat cohesion as a single thing. We say, oh, it's cohesive, it's not cohesive. There are 1, 2, 3, 4, 5, 6, 7 levels of cohesion at class level. So it's not like it's cohesive or not. It's like which level of cohesion, which degree of cohesion my class may have. Don't bother reading all of that because it's difficult to understand anyway. So get the slides later, do some research. I'll just focus on some of them. The worst one, so I put this is, you can find this material somewhere online. I don't even remember where I got that from. But the worst one is methods are grouped arbitrarily and have no significant relationship. Example, a util class. Every single system has a util, right? That's the big bucket of rubbish that we don't know where to put stuff. Put in the util class, right? So that's what we do. I believe that here is a good compromise, where methods are grouped because they work on the same data. So insert, delete, validate, update, and stuff like that. And there is the functional cohesion. That is the best one, when methods grouped because they all contribute to a single well-defined task, like Python and XML. But that doesn't stop there. There are another 6 levels of cohesion at a method level. So let's again just look at some of them. So the coincidental one is when performs multiple operations and sometimes they are not related to each other. And then there is the conditional. According to an if statement, different attributes are modified or different values are set to different attributes. Once again, I think that this is a good compromise where one or more attributes are modified according to only one input. And then functional is the best one, is that 0 or 1 attributes are modified by a method. How many of you use Sonar to give you stats? Right, more than 50%. Sonar has my favorite metric. As I said, like I absolutely love cohesion. So there is a metric in Sonar called LCOM4. That is lack of cohesion of methods. And very rarely we understand how it works. And it's dead simple. So imagine that, for example, I have two methods, get full name, get full address. So this method in here, we operate in 3 of the attributes. This method here, we operate in 2 of the other attributes. And they don't have, they are independent. So this shows cohesion of 2. So imagine that these A, B, C, D, and E, they are methods, and X and Y, they are attributes. So when you have situations like that, that's cohesion 2. When you have situations like that, you have cohesion 1. When you have cohesion that is bigger than 1, that's a good hint that that class or module should be split into 2, for example. And that would also satisfy the single responsibility principle. The opposite of a cohesive class is a God object that does everything. And we cannot talk about cohesion without talking about coupling. So they walk together, as we all know. And coupling is another one that we say, oh yeah, it's loose coupled, tight coupled, and blah, blah. Not as simple. Not as simple. So we have 7 levels of coupling. Right, so when we talk about coupling, we should talk about which level of coupling we have, and not just loose coupled, tight coupled, and all sorts of stuff. Let's focus on some of them. Content coupling. One module modifies or relies on the internal workings of another module, accessing local data and other models kind of stuff. This is, for me, a good compromise, once again. When modules share data through parameters, each datum is an elementary piece, and these are the only data shared. Or the message coupling, that is the lowest one. It can be achieved by state decentralization, as in objects, and component communication done via parameters or message. Normally when you send messages out through events, that's normally when you achieve low coupling. There are 2 other types of coupling. There is the subclass coupling and temporal coupling. So of course subclass, the child class shouldn't know anything about its parents, the parents shouldn't know anything about the child. And temporal coupling is when methods need to be called in a certain order stuff. Tightly coupled systems, they lead to the ripple effect, that one change in one place may be cascaded into chains all over the place. So one way to break the coupling or to achieve coupling without knowing all that 7 levels of stuff is knowing another solid principle called the interface segregation principle. We have a class called employee service that has loads of methods. On its own, as I said before, it's always difficult to judge a design. Is this class well designed? On its own, it's difficult to tell. We need to say, how is this class used by the client? So we may have a finance system, a management system, a HR system. So how do they use them? Do they use all the methods? Because if they do, you can argue that it's okay-ish. But normally, they don't. The service becomes just another bucket of rubbish that you just dump stuff in there because you have no idea where to put stuff. So the interface segregation principle means start decoupling the methods that are used by each system. So if I break that into interfaces like that and make my class to implement all of that, I suddenly have the clients decoupled from the service. And now at this point, that's a very easy change to make. And at this point, I can start splitting this class into 3. Another thing that is interesting about this one, now I'll talk about that slightly later. There is this notion of that is very related to the interface segregation. That is role interface. That was coined by Martin Fowler in 1996, if I'm not wrong. So basically, imagine that you have a system. It's called PERT system. That kind of controls a project management tool that controls dependence between activities, which activities needs to be done first and after, and the dependence among them, all sort of stuff. So you could do this sort of stuff, an interface activity, an activity implementation that has a list of predecessors and successors, or you can start modeling your domain or your concepts, giving names to it, and then you have a list of predecessors and successors. That's the role interface, this one and this one. These lead us to another solid principle, the dependency inversion principle. What it says is that high-level modules should not depend on low-level modules, both should depend on abstractions. And abstractions should not depend upon details, details should depend on abstractions. There is a very curious thing about this diagram. Imagine that, once again, this is a very simple example, but imagine something slightly bigger. This is your core business rules. And at some point, they need some details. Where I'm going to read the data from, where I'm going to write it to, but what I do with that, it's in your core domain. So the execution thread comes from the high-level module towards the dependencies, as you can see with the arrows. And the dependencies relationship also comes in the same direction of the execution thread. A very interesting thing about dependency inversion principle is that we invert these dependencies. As soon as we, for example, if you want to write to a different source or to write to a different output, if we put an abstraction into place, now the execution flow or the execution thread is the same, but the dependencies, they point inwards to the domain. So the execution thread points from the core of the system outwards, but the inversion makes the low-level modules to point inwards, and that's the inversion. And that's easy now to just add new sources or outputs. And then there is this thing about dependency inversion principle, IOC, dependency injection. What are they? Dependency inversion principle is one of the solid principles. IOC is an abstract principle that can be achieved with factories and service locator in slightly different ways. And dependency injection is a design pattern that has a dependent consumer, a definition of dependencies, and an injector. And that's the sort of design pattern that is implemented by Spring and Google Juice and Pico Container and all sort of stuff. So let's give a slightly jump. Encapsulation, very simple concept. So, but when you go into the details, it's not exactly that simple. We normally mention encapsulation as data encapsulations. Oh, I will have my getters in front of my attributes. But there is this concept of information hiding. And this came from David Parnas in 1972. So basically what he says was, hide information about the design from other modules at the points of difficulty or likely to change. So encapsulation is not just about data encapsulation, but is also protected variation that was mentioned by Alistair Cockburn, that is the same as information hiding. It's just protecting your system of the points where they can change more often. So you are encapsulating the details of that behavior, not just the data. And of course, that Craig Larman says that to minimize change impacts, we aim for low coupling. To design for low coupling, we design for protected variation. So encapsulation is also not just putting getters in front of the attributes. And all these inversion of dependency inversion and encapsulation, information hiding, leads to our last solid principle called open-closed principle. So what it means is software entities, classes, modules, functions, etc., should be open for extension, but closed for modifications. So the origins of it is Burton Meyer, once again, 1988. Information hiding, David Parner's 72. Protected variations. OCP, although it came from here, it was put together by Uncle Bob as one of the solid principles here. And Alistair Cockburn, when he coined the protected variations term, he didn't know about OCP or the work from Burton Meyer. That he was the first one to talk about open-closed principle. And the first approach to achieve that was using inheritance and abstract classes. I don't want to go into details, there's too much code in here, but this is like a print report that will print a report of expenses. So without going too much detail, because it doesn't really matter, so it has some data, some instructions related to the way that the report is formatted, but also has a strong dependency of the types of expenses that are being printed, like breakfast, dinner. It will calculate meal expenses if it's one of them. So there's business logic involved in this reporting as well. The types are hard-coded in the reporting. So this is a clear violation of open-closed principle. Why is that? Because if I add a new type of expense, I need to open this code and make the modification. So the idea is that this code is closed to modification and open to extension. That means that I shouldn't be changing a business logic if I just want to slide in a new type. We should be looking for sort of a plug-in mechanism. That would be the open-closed principle. An example of that would be this one. We have our reports, expense reporter, and they are abstracted by the expense class. Even the name of the report that is related to the type of expense could be extracted in an expense namer. And then this line separates my core domain, that in this case is just a report, that has the logic to print a report. But as you can see, the execution thread flows outwards, and the lower level modules, they flow inwards according to the dependency inversion. So I could easily add a new thing without changing that. So this is closed for modification, but open to extension. And this is the cornerstone of good software architecture. Architecture should follow this sort of stuff. When we are doing large-scale architecture, we want to design our systems to be closed for modification, open to extension. That is easy to plug things in. Sometimes it's not easy. We have a new feature, and we feel the urge to open an existing code and make that change. If, for example, we were already processing one of those, and we want to add a second one, before we add this one, we refactor our code, make the right abstractions, and then we prepare the code to receive a new plugin. So that's what we do. So we just take the code, open it, refactor, prepare. Now it's ready just to plug the new feature in. The open-close principle has a side effect, a big one. When you think about all these things, there is a chance that we will be favoring a big design up front. That there is this urge for us to think really, really hard and try to figure out every single thing that could possibly change in my model, and then put these abstractions all over the place. First of all, we don't have a crystal ball. Almost impossible to do that. And even if we had all this time, it has a big price, because all these abstractions and these inversions of control, they have a price, because they make our system slightly more difficult to understand. They are easier to maintain, but they are not so clear as a linear thread. So how do we do that in an agile design? Because this is a misconception, because we say, we think that they are extremes. That the big design up front is that big thing that we do for months and produce loads of documents and all kind of stuff. And agile design is no design. Agile design doesn't mean no design. We need to know where we are going. We need to have a plan. But how do we figure out where to put these abstractions? If you are working on agile fashion, there are a few ways. I'll mention two. One of them, do the simplest thing that could possibly work. Don't put any abstraction. Put that in front of the client. Let them ask for changes. As soon as they ask for change, you identify the areas that are changing your system. And in those areas, you go there and put your abstractions. Another way is, if you don't have clients like that, try to figure out, feature after feature, the areas of your system that you are changing the most. So they will tell you that they are not closed for modification. So if you catch yourself changing the same class, the same function, the same modules over and over again, that's the time that you should abstract that and make that piece of code comply to the OCP. A few unrelated topics, but also in the same domain. Law of Demeter, also known as Principle of Least Astonishment, or least knowledge, or don't talk to strangers, or even train wreck, is when we do this sort of stuff. Object A, dot get B, dot get C, dot get D, dot get E. Does it remember you, like, is there any correlation to functional programming? Bang, map and reduce and select and filter and, yeah. So, sometimes I prefer to deal with 50 lines of imperative code that does 5 things than deal with 5 lines of functional program that does 50. Right? Because how do you test that? Because that's the question that I ask. Both paradigms, they have a big, they are useful. But my main point is, how do I test? How do I make it maintainable? And then there is feature envy. There's another one that is very interesting, more for OO and imperative than functional. Is when you have a client class that goes to an object and say, give me your state, give me your state, give me your state, and then you get all the state out of the object, and then you do a computation on that state. So that means that the client class envies the other class. So, well, in fact, what you wanted to do is say, employee, calculate the monthly salary to be paid, and not getting the state out and do that for you. You just use the tell, don't ask. You tell an object to do something for you. I barely scratched the surface with software design. There are things like CQRS. There is a massive topic on its own. It's extremely difficult to apply. Domain-driven design, I could be here for a month just talking about that. Then the host patterns, TDD, anti-patterns, code smells, missing concept, object orgy. I could be here forever. So I would like to wrap up in terms of, that's what I say is like, there is always a good reason to break a rule, but it really needs to be a good and mainly informed one. You need to understand these principles of good design, and then make an informed decision which ones you're going to break, because follow all these principles. If you try to take every single line of code you write and make it compatible or compliant to every single principle, it's impossible. They will get into contradiction. But it's important that you understand them, have that in the back of your head, so you make an informed decision that in this specific case, I won't comply to that principle, because it doesn't make sense. And then we have some good quote from Craig Larman is, the critical design tool for software development is a mind well educated in design principles. It's not the UML or any other technology. And then Uncle Bob goes on to talk about like most software engineers don't set out to create bad designs. Yet most software eventually degrades to the point where someone will declare the design to be unsound. Why does this happen? Was the design poor to begin with, or did the design actually degrade like a piece of rotten meat? At the heart of this issue is our lack of good working definition of bad design. Regardless which paradigm you are working on, what I'm working on, this was created by Kent Beck many, many years ago. And that was rephrased by quite a few people, like J.B. Rainsberg, Ron Jeffries. Quite a few people rephrased that. That's the combination that I like the most. So I would always strive my code to satisfy these 4 rules in order of importance. First of all, I can test, because that's my main problem with functional programming at the moment. When I'm doing OO, pure OO, I miss my functions. When I'm trying to do pure functional code, I was missing my objects. The main reason that I was missing my objects is that I couldn't bloody test the functional code. So, contains no duplication, maximize clarity. It's like having an expressive domain. Try to express the domain concepts, and has fewer elements. So this 4th is the least important one. I would always, ever favor clarity over less lines of code. Because there's no point in have like 2 lines of code that are cryptic. I would rather have 5. So why is this thing so important? So back to Martin Odersky at the beginning of the talk. I believe that design principles, many of them, they came from the OO world, but that doesn't mean that they don't apply to the function paradigm or other paradigms. So I believe that OO and functional should coexist. I believe that it's too early for me. I don't even have this experience yet. We just started the project in Scala like a month and a half ago. We know nothing about Scala, and we are very bad at functional programming. So we are learning. But hopefully in 1 year's time, I'll be back here or somewhere else, reporting some experience. I believe that OO and function should coexist. My attempt at the moment, and I know that Michael Feather shares the same opinion because we've been talking for a few days, a few weeks ago. I would use, if I had to choose, this is just my try. I'm not saying that's the right thing to do. I would use OO to model my domain and define my flows, my business flows. And I would use functional programming when I have data transformation in very specific tasks. So OO at a higher level, function at a lower level. That's what I'm going to try. If someone has experience in mixing the 2 together, I would absolutely love to hear from you. Currently, they are trying to kick me off the stage, by the way. Currently, we have loads of good literature in design, mainly for object-oriented programming. We don't have a lot for functional yet. I believe in the years to come, you will see more and more people like ourselves, like myself, trying to figure out how to use the 2 together. Can I use functional programming, purely functional programming, in a commercial application, in my web app, in my phone application, expressing business rules? Is it the best tool? Is OO still a good thing? Should I use OO for data transformation and lower level things? Or should I use functional? I think that's what we should be discussing. And not go in the bandwagon and say, oh, function is so cool. Ooh, OO sucks. Ooh, Justin Bieber, I love you. Right? So I think that we should understand the different paradigms, and instead of just like being excited like teenagers with the brand new thing. We are professionals. We should like understand everything, question everything. So if you're interested in craftsmanship, I'm writing the book. It's a linkpub./Socra. So I think that my time is up. If you have any questions, if you want to discuss any other things, please get me outside. I would love to hear from you. Thank you very much.